Hi everyone. I agreed during class on Friday that I would work out the Clausius-Clapeyron problem that we had in GoFormative. Clausius-Clapeyron equation, you'll see it in all different forms, but the form I'm using for this problem, and you can use any of the equations given, they will all work. They have negatives in different places, they have T1, T2 in different places. Again, all the equations are equivalent to each other, and the main trick of getting Clausius-Clapeyron correct is to make sure that the pressure and temperature pairs, the appropriate ones, are kept together. So whatever you assign to P1, and it doesn't matter, you could call either of the two pressures given P1 or P2, as long as you then keep the pairs together. In other words, the temperature that goes with P1 should be called T1, okay? And that's the most common error. So first thing I do in Clausius-Clapeyron is I assign what I'm going to call P1, P2, T1, T2, right? So the first temperature I come to, I'm going to call T1. You could have called it T2, right? So, and the vapor pressure that goes with T1, and I'm reading carefully to make sure, is right here, P1. Okay, and again, you could have called these P2 and T2. You would have gotten the right answer. So let's keep on reading. They're asking for the vapor pressure at a different temperature. So we are trying to solve for P2. And then T2 is this. Now you see in the equation there's a enthalpy of vaporization, which will always have to be given to you. Now the other common error in this equation is keeping track of units, and units are dictated by the R value that you use. So the R value you want to use in the Clausius-Clapeyron equation is 8.314 joules over moles times Kelvin. So it has to be joules. Go back and look at the units that you're given for enthalpy of vaporization. It is kilojoules. So the first thing I'm going to do is match all my units. So I'm going to convert the kilojoules that enthalpy of vaporization is in to joules. Okay, so these common conversions, that metric from one metric unit to another, make sure that you know, okay? So 1 kilo anything is 1,000 of the base unit. All right, so now we have that in joules per mole. And now temperature, as with all gas laws, has to be in Kelvin. And so I'm going to go ahead and convert these two temperatures to Kelvin. So I have 307 Kelvin for T1. All right, and 358 Kelvin is T2. Now I'm ready to plug everything in. Don't forget that minus sign. That's another common thing to leave out accidentally. Okay, be real careful here. T1 is 307 and T2 is 358. All right, so the first thing I'm going to do is simplify the right-hand side of this equality. And I'm going to do it stepwise so that if you do end up making a math error, you can go back and see perhaps where it was. So I'm doing inside the parentheses right now. And I'm carrying a bunch of extra digits, and I'll explain why, but it's especially important not to artificially truncate a round too early in this type of calculation. All right, so in that parentheses, I get, all right, and now I'm going to go ahead and multiply it by this ratio. Don't forget the negative. All right, so the entire right-hand side, I'm going to change colors here. So the entire right-hand side of this equation, I get minus 2.270. All right, so now I need a new page. So at this point, we have natural log of 40.1 divided by P2 equals minus 2.270. To get rid of natural log, you are going to look for the e to the x button on your calculator, and you're going to, both sides of this equation become an exponent for e. That is, so e is considered the anti-log of a natural log. All right, so now the natural log goes away on that side, and we now have 40.1 divided by P2 equals e to the minus 2.270. So hopefully you have found your e to the x key. Sometimes it's a second function above your ln, natural logarithm key. But when you do find it and you put this in, the value that you should get is 0.1033. Now, for those of you who are not good friends with algebra, be careful simplifying this to solve for P2. Notice P2 is in the denominator. It's got to be in the numerator to isolate it and solve for it. So I think most of you are taught to cross multiply, but in any case, what you should end up with, P2 equals 40.1 divided by 0.1033. And that gives you your final answer, putting it in my calculator, of, well, I got 388 with the sig figs that I carried, okay? So there are a variety of things that'll make your answer vary slightly. So I would say, you know, if you got between about 385 to probably 395, you're fine. I would say if you got outside of that range, go back and see where perhaps you rounded too much. Now, some things that will make a difference when you're converting to Kelvin, I just use 273. If you use 273.15, you're more precise than I am, okay? So that's, but the more important thing to be careful is when you're doing all the intermediate simplifications, like you should have 4 or 5 or 6 digits in this exponent. And because the reason it's so sensitive is because this final value is actually an exponent, any little difference in that is going to have a significant impact on your final answer. For example, let's say that you decided to round this exponent to minus 2.3, so that you had e to the minus 2.3. Guess what your final answer would have been? That would have brought up all the way to 400 torr, okay? So you get my gist here, again, since it's an exponent. So carry a bunch of extra digits so that you don't get thrown off by that. And that is it.